You don't have to travel very deep in the oceans before survival becomes a challenge. Pressure increases rapidly below 200 meters. The light of the sun becomes but a faint glow, and at 1,000 meters down, the midnight zone is bathed in darkness. Temperatures here drop to a chilling 4 degrees Celsius, which is 39 Fahrenheit, and this persists all year long with no seasonal fluctuations. Any changes in the weather above will not be felt this far down. And yet, even in this bitter, uninviting world of cold shadows, a myriad of peculiar creatures have made their homes, dramatically altering their anatomy, behaviors and physiologies in order to cope with the challenge of living here. In this film, we'll take a look at the unique ways in which these otherworldly creatures have adapted to thrive as masters of the deep, dark sea. Anatomical adaptations relate to the physical features of an animal. Its size, shape, body color and features that make different species appear distinct from one another. These are the result of evolution. Often adaptations occur because a gene mutates randomly. Some mutations will hinder a creature's survival, but occasionally it can help an animal survive better than others in the species without the mutation. The beneficial characteristic allows the mutated individual to be more successful, so allowing it to survive and reproduce, passing on the adaptation to its offspring. This process is the driving force behind speciation and biodiversity. And it is the reason why marine life is so diverse and abundant, allowing organisms to change dramatically in order to inhabit different environments. Perhaps the most obvious difference between creatures of the deep sea and those from the shallows can be highlighted by comparing their pigmentation. In the shallows, animals make the most of the available light by displaying brightly colored bodies for communication, defense or courtship. We find cuttlefish showing off a pulsating array of patterns to attract partners, and reef fish using their conspicuous complexions to identify one another among the complex coral gardens. But in the deep, the lack of light means inhabitants must use their body colors in an entirely different way. They make themselves invisible, favoring darker colors like black or even red on account of the fact that red light is filtered out in deeper waters. As a result, creatures like the vampire squid can traverse the depths unseen by predators. Some invertebrates take this adaptation to the next level, making themselves transparent, like this deep-sea amphipod on the open ocean currents. But with so many species having evolved to conceal themselves amidst the darkness, deep-sea predators have had to adapt in equally unusual ways in order to hunt prey. The result in many cases is large, bulbous eyes. Take a look at those of the barrel eye, a fish with extraordinarily light-sensitive eyes that can rotate within a transparent, fluid-filled shield on its head. But this doesn't seem to make much sense. We already established the fact that beneath 1,000 meters, there is no residual sunlight to illuminate the depths. So, one might deem the presence of eyes in deep-dwelling species to be unnecessary. But in fact, the sensitive eyes of these creatures are not for making their entire surroundings visible. They are present for another purpose, to spot the bioluminescence of other deep-sea creatures, a physiological adaptation that we'll examine in greater depth later on in this video. Alongside the prevalence of dark or transparent bodies, we can observe a number of other trends in anatomical adaptations that appear to be advantageous in the deep. Many animals are frail and weak, and their body is thin and flabby to help cope with extreme pressure. Deep-sea fish are slender and delicate. In many species, their tail has become long and whip-like, as seen in the chimera. Weak jaws are common in the deep sea. Many organisms live on decaying oozes or rotting carrion, so they generally lose their powers of mastication. In deep-sea sharks, 6 or 7 gill slits are favored instead of the typical 5, a characteristic that endures from their early primitive ancestors. The low oxygen levels found down here make having extra gill slits advantageous. One adaptation that appears to be shared among almost all deep-sea creatures, particularly invertebrates, arises from the need to become more efficient. Food is scarce, and there is little oxygen, necessitating the tendency of deep-sea creatures to become far larger than their shallow water counterparts, a phenomenon known as abyssal gigantism. Amphipods that grow no larger than a few millimeters in the shallows can here reach extraordinary sizes. The supergiant amphipod grows to be 34 centimeters or 13 inches long, and the giant isopod, resembling garden woodlice, has been observed at a meter long, which is about 2.5 feet. The largest size of the giant isopod may be an adaptation that allows it to quickly and efficiently monopolize food in the deep sea. Generally, a bigger body size is advantageous because it decreases their surface area to volume ratio. This minimizes the loss of heat energy to their surroundings, slowing their metabolism and allowing them to survive for very long periods of time without eating. In the starved depths, efficiency is key. While anatomical adaptations relate to the physical features of an organism, physiological adaptations instead pertain to internal body processes. This can include releasing toxins or poisons, secreting mucus to deter predators, and controlling chemical reactions within cells to help with survival. Bioluminescence is perhaps the most common physiological adaptation found in the deep sea. Surprisingly, the deep ocean is not entirely starved of light. Many creatures take advantage of the inky darkness, producing their own light to communicate with one another. It works by creatures controlling the mixing of chemical compounds, initiating a reaction that produces light energy within their body, an invaluable ability that opens up countless possibilities for communication, camouflage, and mimicry. Shoals of shimmering firefly squid use their bioluminescence to blend in with changing light levels as they rise to feed at the surface. The higher they go, the brighter their surroundings, so they slowly increase the intensity of their lights to match the ambient light, a phenomenon called counterillumination, which can also be considered partly a behavioral adaptation. In the depths of polar regions, certain fish species, like the ice dragonfish, are able to produce antifreeze proteins in their blood, stopping them from freezing to death. Without this ability, fish would be unable to inhabit many of the extreme environments of the depths. This goes to show how just one adaptation can open up a world of opportunity for organisms and influence the overall diversity of the deep sea dramatically. But it's not enough for organisms to simply rely on their anatomy or chemistry to survive. They must also adapt their way of life and change how they interact with their environment and fellow denizens of the deep. The adaptations that develop in the deep sea are not only dependent on the abiotic, non-living factors like pressure and temperature. They are also determined by the biotic factors relating to the presence of other organisms that may be potential predators, food, mates, competitors, or symbionts. In particular, these ecological interactions influence the behavioral adaptations of organisms, that is, the things they do to survive. For example, the migratory behavior of whales chasing krill blooms that are passed down through generations, or the diverse feeding behaviors of sharks. Just like we saw with the anatomy of deep-sea creatures, we find similar behaviors arising in vastly different species in response to the same conditions. The scarcity of food leaves very few options when it comes to feeding mechanisms. Creatures can't always count on the presence of prey to sustain them, so they must make use of another food source: marine snow. Marine snow is a constant trickle of dead organic matter sinking from the productive waters above, a concoction of carrion, excrement and shells, which to any opportunistic organism is vital for survival. In order to make the most of it, creatures have altered their behaviors in a number of ways. Pelagic polychaete worms use mucus to build expansive nets around themselves in order to catch copious amounts of sinking material. The vampire squid extends a tentacle out into the snowfall, bringing captured flakes back to its mouth. Animals on the sea floor exhibit different behaviors compared to those residing in the mid-water zone. Rather than catching the material as it sinks, they feast on the marine snow once it's settled on the bottom. Here, benthic burrowers like sea cucumbers shovel sediments into their mouths to get at the nutrients. They are scavengers like many deep-sea creatures. In addition to feeding behaviors, there are commonalities in the ways in which organisms move around in the deep. Zooplankton, a staple of the marine food web, follows specific patterns of movement. As a result, the migrations of innumerable predator species have become synchronized, leading to the mass movement known as diel vertical migration. At night, 5 billion metric tons of organisms rise to the surface in pursuit of plankton. These behaviors represent the ability of organisms to take charge of their own fate. It may be true that anatomy dictates much of what an organism is capable of, but by adopting certain behaviors and altering their ways of life, deep-sea creatures are able to be stronger competitors in the unending conflict for food. Adaptations are the key to speciation and biodiversity, for it is the abundance of different characteristics that allow organisms to thrive in every corner of the oceans. The deep sea is nature's experiment, a concoction of curious creatures with unexpected body forms, behaviors and physiologies. It has created a world of the weird and wonderful, defined by glowing life forms and gelatinous beings that would seem out of place in any other environment. But here, they are masters of the strange, changing in extreme ways in response to an extreme environment.